Okay, here we go. Right, thank you everyone. What I'm going to talk to you about today is just how on Earth we can tell what Mars is made of. I'm James Scott and I'm the President of the GSNZ Society, and this is my talk to the Bay of Plenty branch. What we've got in the background of this slide here is the highest mountain or volcano in the solar system, and that's Olympus Mons on Mars. It stands at about 22 kilometers high, so it's significantly higher than anything we have on Earth. And that's one of the features that makes Mars different to Earth. But in fact, there are a number of different features, and I'll run through them in this talk. So I should point out that I'm based in Dunedin, and this image here is the classic Dunedin that most of you will be familiar with. Lovely weather, blue sky, and we can ignore all that. Oh, there's the waves crashing. It's St. Clair Beach. But from Earth today, we can see the moon. And you can see it up in the center there. Now, I took this image with my mobile phone one evening when I was out for dinner. You can zoom in and you can sort of see some of the moon features. Now, when we look at the moon today, we can actually make out a number of the features on the surface. So, for example, the black patches on the moon represent very large asteroid impacts. Probably early on in the moon's history, the largest crater there is about 1,000 kilometers in diameter. And these have then filled with an igneous rock called basalt, which is what gives it the black coloration. But the point is that from Earth, we can clearly see what the surface of the moon is like. Perhaps not in this image, but if you had a telescope, you would be able to do so. So one morning I was biking to work, and again, you know, it's a beautiful Dunedin day with no clouds in the sky, and you can make out the moon up here. It's a bit of a crescent shape at the time I took this photograph, but there was a very bright star beside it where my cursor is. And I thought to myself, well, it was quite early on in the morning. It was on May the 3rd, and it was just after 7 o'clock, and I had to do some teaching at 8 o'clock. So I had to be there a little bit early. And I thought to myself, I wonder what star that is. And it turns out that you can go to a website called timeanddate.com, and you can roughly, it sort of picks up your IP address and works out where you are, and then you can bend the perspective around to show the night sky. And you can see here that that bright star is Venus. There it is, Venus, and there is the crescent of the moon, and this is the ecliptic plane here, which the planets lie on. So at 7:15 in the morning, we can see Venus from Earth. Venus is from Earth, and then there'll be Mercury after that. And indeed, had I been up a little bit earlier, you can see the time down here, 20 minutes earlier, I should have actually been able to see Mercury there as well. So we can see planets from Earth quite clearly. And in fact, if you this image here I took just a couple of days ago. I was on the west coast of the South Island. It's not a very good image again because I was using my phone, but you can see that there is the moon down there. This is Venus, this bright spot just here. It's and if you were to go out tonight, I'm not sure what the weather's like in the Bay of Plenty, but if you were to go out tonight, you would also likely be able to see Venus as the brightest star in the sky. But up here was Jupiter. So that's two planets that we can see from one site. And indeed, it's actually possible to see Saturn as well. Well, it's a little bit unclear in this image, but these three planets all lined up at the same point, and they lie on the ecliptic plane. So that's the plane which the planets orbit around the sun, including ourselves. So we can see these various things from Earth. Now, I don't know if any of you have tried, but you can actually also see Mars from Earth. It often comes up as a bright star, but with a slightly reddish hue. Now, this isn't a view from Earth, of course. You can kind of get a clue from where this is down here. You've got a bit of a Google here, but if you ever go to Google Earth, you can toggle a button at the top and you can look at Google Mars. And this here is Mars. And we have had sufficient orbiters going around the surface photographing the surface of Mars that there's actually a pretty good record of what it is. You can see a number of craters on the surface. Oops, sorry. You can see a number of craters on the surface. Some of them are quite large. So we can see Mars. We can see see most of the planets without a telescope, but of course, to see the details, we need a telescope or imagery of something that's gone past it. So here are some questions for you. If we were in a crowd, I would ask you directly these questions, but if anyone's feeling bold, how many missions have there been to Mars? Feel free to give me a number. Unmute yourself and give me a number if anyone's got a feeling for that. Well, unless you're yelling at your computer screens on mute, it seems that you're probably a little bit unclear of how many missions have been to Mars. So you're probably unclear on the percentage of which have failed. And failed is by the mission hasn't achieved its goals. And probably the question that you can all get is how many of these missions have returned? So here we go. We've actually had 49 missions to Mars since 1960. And the three most recent ones are the Tianwen mission in China and the Emirates Mars mission, which is the UAE and Japan, a joint where Japan provided the technology and the UAE provided the drive for the trip. And the most familiar one, I would guess for many of you, would be the Perseverance mission. And that's a NASA mission led by the United States. And it has a rover on the surface called Perseverance at the moment. So they all took off, and I think it was about July last year. And in a very small window when COVID was actually affecting large areas of China. I'm not sure where the Emirates mission was launched from, but certainly was affecting the United States. And so these three missions all launched at a very short window with the goal of getting to Mars as quickly as possible. And that particular window, this 2-week window, and I think it was July last year, enabled these missions to get to Mars as the shortest distance for several years. So there was a real drive to get these missions launched. Now, of those 49 missions, greater than 50% of them have failed. And we should recognize, though, that the chances of success are improving rapidly because the first 11 missions, most of which were actually Russian, failed. So the Russians and the Americans really drove forward the Mars exploration. But in the 1970s and around that period of time, the chances of having a successful mission to Mars were very, very low. And so they were sort of, well, you can see that 11 of the first 14 missions failed, which is an awful lot of money spent. Of the missions that have failed, one of the best known ones is one which was a United States mission where they failed to convert miles to kilometers upon bringing the spaceship into the Martian atmosphere, and so they missed their ability to land, and the spaceship just simply burnt up. So that was a fairly classic mistake. And the third question, which is how many of these have returned, and we've got 0 return missions to date, although there are some planned in the future. So here are some facts about Mars. Now, we'll do this in kilometers. So Earth has a diameter of around 12,756 kilometers at the equator and slightly smaller at the poles as a result of its compression as it spins. But Mars, you know, the planet that's proposed to be our savior, is tiny compared to Earth. It's actually only about 1/8 the size of Earth. Look at the diameter there. The diameter is just under 7,000 kilometers, and the diameter here is just under 13,000. So Mars sits in size somewhere between the Earth and the Moon. Mars itself has two moons. They're called Phobos and Deimos, and they're really, really small. One is 22 kilometers in diameter, and the other is 12 kilometers. And they're probably asteroids that have been captured as they've passed close to Mars and been captured in that gravitational field. You can see there that a Martian day is fairly close to an Earth length day. That's the length of time it takes to rotate. So unlike Earth, a day is called a sol, and a sol on Mars is 24 hours and 39 minutes and 35 seconds. But since Mars is further from the sun than Earth, it takes many more sols, or many more days, for Mars to do one complete rotation of the sun. So it takes almost 700 days to orbit the sun. And just an interesting feature is that the sunsets are blue. You can see that if you go on to the NASA website and look at some of the Curiosity rover images. So as an example of the distance from the diameter of Mars, the distance from Bali to Dunedin is about the same as the diameter of Mars. So it's really not a very large planet at all. Now on Earth, we have a relatively good idea of the internal structure. And I like to use this picture here of an onion skin, or an onion sitting down here, to sort of show the Earth is made of a series of different layers. The innermost portion is solid. That's the inner core. You can see this is a pizza slice, or a with a radius of Earth of around 6,500 kilometers. The inner core is a solid portion in here. Within the interior of Earth, the only place that's consistently liquid is the outer core. And you can see the Earth's core stretches is about half the radius. So the core from the surface to the core is just under 3,000 kilometers. From the core to the very central point of Earth is just over 3,000 kilometers as well. Now, above the core, we have a mantle. And the mantle has a series of different layers in it, which aren't really important for this particular talk, but it is a rock type that's mostly solid. And then sitting on top of the mantle is the crust. And the crust is basically, if you look at the scale, look at the thickness of the crust, the average continental crust is actually about 30 kilometers thick. And in the oceans, the crust is about 5 kilometers thick, typically. So the crust, what we live on, is really the scum on the surface of the planet, which is otherwise made of a core and a mantle. So that puts us in some perspective. If we had a globe in front of us of the Earth and we ran our finger around it, we wouldn't be able to feel the topography if it was scaled to that globe. Even the Himalayas, we wouldn't be able to detect that with our finger if we ran it around that globe. So in planets, the crust is actually fairly insignificant. It's just a layer on the outside to a planet that's largely, at least the rocky and terrestrial planets of the inner solar system, Mercury, Venus, Earth, and Mars, is solid. It's that rocky interior portion made up of a core and a mantle. Now, what we do know about Mars is that it has a layered interior as well, but the distances are much more uncertain. So, here the crust may be up to 60 kilometers thick, but there's a plus or minus. Is it 60 plus or minus 30 kilometers? That's pretty inaccurate. The core, solid, question mark, liquid, question mark. Well, that question's actually rather recently been answered, and I'll touch on that in a moment. And then there are some discontinuities within the mantle as well. But their elevation, their distances from the center are unclear as well. So Earth, we have a pretty good understanding of the interior. We have plenty of rocks that come from portions of the interior. But Mars is more like, well, we kind of have an idea, but it's a bit of a blurry perspective. Now, I pointed out before that Mars is about 1/8 the size of Earth. If I just go back, you can see that if Mars is much smaller in total, then its core must be much smaller as well. And this has an effect on the gravity of the planet. So here we've got the highest point in the solar system, or from the surface, which is Olympus Mons, 22 kilometers tall. By comparison, Mount Everest on Earth, our highest point, is just over 8,800 meters. So on Earth, we can support mountains up to, let's say, 9,000 meters high, 9 kilometers high. Earth would not be able to support a mountain the height of Olympus Mons. Now, the way it works is that the gravity on Earth, which we're accustomed to and our bodies are accustomed to, is different, would be different for us on Mars. With a smaller core, it has a weaker gravitational field. And so if we were standing on the surface of Mars right now, we would feel that reduced gravity. It's about 40% that of Earth. And the effect of this is that the mountains can become higher. And how to explain this is that if I were standing on the surface of Mars, I could probably relatively easily support you on my shoulders and walk around, because on Mars, because our weight is a function of gravity, then my reduced weight means that, and your reduced weight means that I could carry you around. And so the mountains can be higher. Mars is capable of sustaining higher mountains than Earth is, because it's sort of confusingly, because it's smaller, because it has a weaker gravitational field. So weaker gravity, higher mountains. This is a satellite image of the surface of Mars, and we've got Olympus Mons sitting out here. This high topography here, the brighter the color, the higher the topography, is called the Tharsis bulge, and it represents an elevated surface on Mars. So we can see that Olympus Mons, which is colored white and then with red around it, white. You can see the altitude here goes from 0, which would be 0 kilometers, which is as if Mars were a sphere, goes right up to around 22 kilometers high. This fracture running through the surface here is called Valles Marineris. And if we were standing on the edge of this fracture, let's just pick a point about here. It's pink. So we can look at our elevation. So from a sphere, it would be around 6 kilometers high from the surface. And in the inside here, we can see that that's a greenish color. So that's 2 kilometers beneath the surface. So if we were standing on the lip of this large fracture, we would be looking down an 8-kilometer deep trench into the ground. The height of, just under the height of Mount Everest, we'd be looking down into the bottom of this, this fracture. Now, what I think is particularly neat about this image is that the higher topography here has these channels running off into the lower topography. You can see the same here. Higher topography, there's a channel, and it comes down here and sort of sweeps around here. And these features look for all the world like river canyons. Or they're quite large on here, and they probably represent incremental floods and flood events that took place. But the question of whether there was water on Mars has now been, I mean, I'm not claiming I'm answering it, but it's now known that unequivocally that there was water on the surface of Mars. And these images confirm these as river channels into a lower topography, which quite possibly was a sea. We can kind of get another perspective. This is the other side of Mars. And you can see that there are these large divots in the surface. And these represent gigantic, hopefully you're all thinking of it, they're gigantic asteroid or meteorite impacts on the surface. And if this one here we look at, you can see that its depth, it's sort of a purpley color. So let's say -7 kilometers. It's green here, -2 up to yellow. So that impact there is about 8 kilometers deep as well. In fact, if you look at the surface, it's very cratered. There are heaps of them scattered all over. I think the estimate is that there's something like 40,000 different craters on the surface. So this is a surface that has been bombarded for a long time by debris from space. This image here, which I've turned upside down, so the letters are upside down to kind of match the previous image of the higher topography, and the lower topography shows the two features on it. Blue represents valleys. So you can see that there are a number of lower portions on the Martian surface. You can also see that these dots, and these have been imaged by orbiters flying around the surface, have been determined to be clay. In Dunedin, we've got plenty of clay, and for those of us that are familiar with clay, will recognize that clays form by breaking down of rocks. They form by weathering of rocks in the presence of, hopefully you've guessed it, in the presence of water. So the occurrence of these minerals scattering the surface of Mars in these valley areas very much indicates that water was present on the surface. Now, today, that would be a problem because the average temperature is, you can see it here, is about minus 63 degrees Celsius. But to have water active on the surface and eroding the rocks, the temperature must have been greater than 0. So it's been suggested that Mars had relatively short-lived warm periods which enabled erosion to take place. We can look at the, we can see that Mars has ice on the surface. It also has frosts, it has clouds, not quite the same clouds that we have on Earth, they're thinner, and you can see the frost, there's the ice sheet there, this is a real image of a crater. Here is some of the frost scattered around. It clearly has frozen water on the surface. It just doesn't have very much of it, which, as I'll point out later, is a problem for life. So this is an artist's interpretation, and they've shown that Mars was probably almost half underwater at some point very early on in its history. It's suggested geologically this was probably about 4 billion years ago. So around 4 billion years ago, there were probably 2 blue planets in our solar system. There was Mars and Earth. So we had 2 planets that had liquid H2O on the surface, Mars and Earth. This area here is pretty well cratered, and so it suggests that this ocean would have been present early on, because otherwise it would probably erode the craters that formed. Well, Mars clearly doesn't have an ocean on it today, and that makes it quite different from Earth. But another feature that's very different is that this is Earth on the left-hand side here. These are the magnetic field that's protecting it from the solar wind, the radiation from the sun. And you can see here is the north and the south pole with the magnetic curves around it, and it kind of forms a protective shield around the planet. Now, it's known that Mars has lost its magnetosphere. That's the name of that surface protecting it. So it's constantly being bombarded by radiation. Now, the reason that Mars has lost its ocean is suggested to have been that it also lost its magnetosphere very early on in its history. And the result of that was that the atmosphere was able to be lost and the water largely evaporated. And that's left a surface, or a weak atmosphere, that's very, very rich in carbon dioxide, which is heavier than water. So Mars has lost a lot of water into the solar system, and it's constantly bombarded by the solar wind, which is radiation, and that's really not very good for life at present. This diagram here, it's a little bit stretched. Of course, Mars isn't a square, so the poles look very large, but here is water ice on the surface. You can have other different types of ice, and other planets further out from the sun have have different kinds of ice, including methane and nitrogen ice on the surface. But Mars largely has water ice on it. This is a NASA diagram, and you can tell that because only the NASA missions are shown on it. None of the Russian missions are shown on it. And it's not entirely up to date because it doesn't show the Perseverance mission, which is the most recent one. But I'll draw your attention to a couple of them. One of them is InSight, and the other is Curiosity. These other missions are earlier. Opportunity was a rover, and these ones were early as well. Now, these particular sites have all been picked for a particular reason. They're very, very expensive, and as I pointed out earlier on, they often fail. So all of these missions have to have a particular target when they're launched from Earth. And it's possible for people to control their rockets and deployment of these, that they land in precisely the place they're intended to land. So InSight, for example, is located almost on the equator. And all of these will have had sites that were picked for good, pretty much geological reasons. In fact, that's actually an important point to make, is that Mars is the one planet in the solar system that's been colonized by robot geologists. This is Curiosity. That's one of the active rovers on the surface, and it's taking a selfie of itself. It has a robotic arm. It doesn't look like it's taking a selfie, but it has the ability to stitch a series of photographs together. And this is one of them. It's a six-wheeled robot, and you can see it's got quite dusty in here, but it has a variety of equipment on it for analyzing the rock. So this is one of our robot geologist colonists. Now, most people who saw this photo were interested in the rover, but I'm a geologist, and so we ignore the rover and we can look at the rocks in the background. So this is just a zoom in detail into the back of that photograph. And you can see that where this rover is rolling around, there are layered rocks in here. And these layered rocks would be very similar to what you would find at the bottom of a lake. In the North Island, if you were to go to the bottom of Lake Taupo, you would find delicately laminated sedimentary rocks. So just go back, we can see here that, and they're all over the place. It's a little bit distorted because of the way the camera has taken the image. This crater, which it's located in, called the Gale crater, which has some high points, which might be an old volcano here. But this crater has lake sediments, delicately laminated lake sediments in it. You can actually also see that the drill piece has analyzed some of those sediments down there. It's drilled down, and that's what that little hole is in the ground. So, you know, this has provided further evidence for there being water on Mars, and quite widespread as well. The other mission that's currently, or another mission that's currently active, is the Mars InSight mission. And its task was to establish whether there are Marsquakes. Well, we would call them earthquakes on Earth, and the moon has moonquakes, and Mars predictably should have Marsquakes. So it's got two pieces of deployment. It's got this here is a heat probe that goes down around 5 meters into the surface, and its idea is that it can measure the temperature of the interior of Mars and get an idea of what the geotherm would be. That's how the heat is distributed through the planet. It's also got a seismometer located here. They're attached to this the InSight deployed vessel, which doesn't have wheels, so this is where it landed. It's got 2 large solar panels. And on Earth, hopefully you'll know what a seismometer is for. It's for detecting earthquakes. So on Mars, the idea of this is that its goal is to detect whether there are Marsquakes. On Earth, an earthquake represents tectonic processes. It represents where 2 plates are moving together, or where magma is interacting with the surface. I'm sure many of you are aware of that in the Bay of Plenty. So the goal of this is to see what's happening inside Mars. And if they can pick up some Marsquakes, there's the ability to try and establish what the interior composition is and the depth of various changes, like from when the core changes to the mantle. On the 128th day that it was deployed, it actually felt a Marsquake. So the point of this is that the interior of this planet is not dead. It's still slightly active. Again, here's a real image from the surface. You can see that it looks pretty wasteland. It's very dry. Obviously, it's very dry. There's lots of rocks on the surface. They're scattered around and they're affected by wind. And we can see the solar panel, and there's something radioactive on here. And this is the robotic arm that comes out off the InSight mission. Okay, a little bit blurry, but it looks a bit like a desert. You could imagine some of the drier portions of, say, the deserts on Earth is looking very similar to this. So a couple of months ago, or a month or two ago, there were several papers published as a result of the InSight mission. The first papers were published reporting their results. And what they were actually able to do is provide some of the best information that we've had for ever on the interior of the planet. They managed to image faint signals bouncing off the core. And that told the authors of that the core was about 60 kilometers beneath the surface. And this is kind of significant because from Earth, we can estimate the mass and the moment of inertia of mass fairly straightforwardly. And this implies that Mars's core must be slightly different to Earth's. That is, it's slightly less dense than Earth's core. Now, Earth's core is dominated by iron with a little bit of nickel, and a few other elements in it too, but Mars must have more of these other elements embedded in it. They also found that the core is still partly liquid. So it's not solidified yet, it still has a bit of life left in it. There's more detail there, but we'll keep moving on. The point of it is that by deploying this seismometer, that they've finally been able to determine more about the interior of Mars, and they did actually manage to image some of the discontinuities that occur within the mantle between the core and the crust. So, Mars, what is it composed of? How old is the surface, and how does it compare to Earth? Sort of part two of the talk. Well, we have no return missions from Mars, yet, as I said before, we actually have rocks from Mars on Earth. And when I put this talk together, there were 260 known different Martian meteorites on Earth. And you're saying, well, how would you know that you've got a Martian meteorite on Earth? And how would you go about finding one? Well, most of the Martian meteorites come from the deserts of Africa. And that's because these meteorites, when they come in through our atmosphere, they get a black fusion crust. They burn up a little bit. And a black rock sitting in a pale colored desert stands out very well. And in northern Africa, there are plenty of people who travel through the deserts, and they're well aware that if they find a meteorite, they can sell it to a meteorite dealer, who will then proceed to cut it up and sell it on at a higher price to people around the world. So the deserts of Africa are very common, or relatively common, for finding Martian meteorites. But there's another place that they're common as well too. And where might that be? Where would a black rock stand out? Well, it stands out on ice particularly well. And so Greenland, the Greenland ice sheet, a meteorite that lands on the surface of Greenland will stand out. That's a common place for them. And also Antarctica. And every year there are missions that go to Antarctica, and they go to places where the glaciers move debris, but they get to stagnant areas where those glaciers the ice sort of stops flowing and collects rocks. And so these missions go there and they're able to pick up meteorites off the surface. And then with some detective work, you can work out that they come from Mars. And I'll explain that in a moment. Just go back before I get to that slide. So the reason that we have Martian meteorites is that they're blasted off the surface. We saw before that Mars was very, very cratered. That means that there are impacts, or there are meteorites striking the surface of Mars quite regularly. And you can imagine that when a meteorite strikes the surface, it actually has the ability of evacuating or ejecting material from that surface. And if it can escape the gravity of the planet, and as I pointed out before, Mars has a weak gravity, then it has the ability to travel through space, and eventually will intercept Earth's atmosphere and land on the surface. Or potentially burn up, probably a lot burn up, and many of them land in the ocean as well. So what we see on Earth is really a fragment of the debris that comes through. But there are these Martian meteorites caused by other meteorites hitting the surface of Mars and ejecting that material. So what's the key concept here is a thing called escape velocity. On Earth, if we have a rocket, we want to take that rocket and get that rocket out of the Earth's gravitational field, it needs to be traveling, this is in miles per hour, but it needs to be traveling at around 25,000 miles per hour. That translates to, I think, about 36,000 kilometers per hour. So our rocket has to be going very, very fast. On Jupiter, our rocket, to get out of Jupiter, which is very large, it has a very strong gravitational field, our rocket would have to be going a cool 134,000 miles per hour. Mercury, the smallest planet in the solar system, our rocket needs to be going around 10,000 miles per hour. And Venus, which is the same size as Earth, or very similar in size to Earth, about the same as Earth. But here's Mars. Our rocket, or our rock, to escape the gravitational field would have to be going around 11,000 miles per hour. And this is the concept of escape velocity. That's how fast our rock has to get to escape Mars. And that velocity is dependent on the planet mass and its radius. And eventually, these things land on Earth, and somehow they make their way into interested people's offices. And so here are the first three Martian meteorites that I managed to get my hands on. They're all arrowed here, so this is a large fragment. They're sitting in a glue because it's easier to analyze them when they've got a glue. Here's a smaller one. You can see here's millimeters along here, so that's about 5 millimeters. Centimeters long here, it's about 5 millimeters, and then this one here is just a very small little fragment, actually slightly under the arrowhead. Now, I said before that these meteorites are actually relatively easy to find. And the first of these, the smallest one actually, I found in a gem store. I've never actually properly collected a meteorite. I've only ever found them in stores or online. But this first one I found it in a gem store in Akaroa. I mean, I was totally unexpecting to find a meteorite there. I had gone in because my wife had gone in, and she'd said that I probably would like the store, and I said I'm not really into gems, I'm into rocks, but I sort of came in anyway, and there was a little cabinet there, and this cabinet had meteorites, and one of the meteorites said fragment of Mars, and it looked a little bit like this. I'm not sure if you can see me or not. Maybe we can show these later, but I had a little container, and the little container had a fragment, so it says this has a certified number on it, which is a particular unique identifier of that particular meteorite. And so I took it to my university, I purchased it, I took it to the university, and I analyzed the mineralogy and the chemical composition of it. And lo and behold, it was actually a Martian meteorite. And then I realized I could buy them on eBay and various other meteorite stores, and so I've purchased more of these meteorites subsequently. So you too could own a piece of Mars if you wanted. You'd be able to get this from you'd be able to get one online. Personally, I think they make quite good Christmas presents. People are quite impressed by the ability to be actually able to hold another planet. I mean, that's it. I get to hold, at my work, I get to hold rocks that are from another planet. That's pretty cool. When you look at these particular rocks, we find out that they're mainly a rock type called basalt. And basalt is something that many of you will have heard of on Earth. It's a very common volcanic rock. So the surface of Mars appears to be dominantly volcanic. We kind of knew that already. You know, Olympus Mons is a volcano, and there are other volcanic features, but the samples that are coming back as meteorites are basalt. So we can actually look very in detail at these particular rocks and see the minerals. And we find that those minerals are very similar to what we find on Earth in basalts. Now, the question you should be asking is, how do we know that they come from Mars? Why could you not just go to somewhere in the Bay of Plenty? There's probably basalt up there, collect a little bit, stick it on eBay, call it a Martian meteorite. Well, the reason, there are several reasons, but one of the most prominent one is that the gas abundances within these meteorites. So what we have today is we know the composition of the Martian atmosphere that's up here. And this is the composition of Earth's atmosphere. So Earth, we know of as being rich, we know to be rich in nitrogen, oxygen. So nitrogen is N2, oxygen, a little bit of argon, and this number here that we're worried about, carbon dioxide at 400 parts per million. Well, actually it's slightly higher than that now, 412, I think. But if we look at the Martian abundances, we see that the atmosphere is dominated by carbon dioxide. About 95% of the atmospheric gas is carbon dioxide. Nitrogen is a small component and oxygen is very, very small. And there's a bit of argon as well. Now, we know this because there are orbiters and also landers that have measured the composition of that Martian atmosphere. So when one of these meteorites ends up on Earth and somebody's trying to interrogate whether it could come from Mars, they can measure the gas compositions that are trapped inside the meteorite. So when this rock was blasted off the surface, this one here, when it was blasted off the surface, it partially melted. It was so hot that some of the minerals melted, and it trapped little vesicles or little gas bubbles of Martian atmosphere. And when it comes back to Earth, those gas bubbles can be measured in a laboratory and compared with the known Martian atmosphere measured by the orbiters. So this diagram here has the Martian atmosphere on the y-axis, and it has the numbers are irrelevant at the moment, and it has the glass composition. Shergotite is just a particular type of Martian basalt named after a place called Shergoti, where the first Martian basalt rock was discovered. But this is a measurement of the glass inside one of those meteorites. That's the material that contains the bubbles, the gas bubbles. And you can see that, for example, this number 11 in the glass is matched by 11 for the atmosphere. So the abundance of krypton in our meteorite has, or this line is a one-to-one relationship of the atmosphere versus the rock. And so if our gases, so xenon, krypton, neon, argon 36, and then argon 40, nitrogen and CO2, if these gases in our glass match the atmosphere, there's simply no other place in the solar system that they could come from. These rocks have to come from Mars. And there are other isotopic properties that distinguish them as well, but this was one of the first and most straightforward methods of determining that. So we 100% have Martian rocks on Earth. This here, I won't dwell on this too long. The bright colors represent different minerals. This is you can see the scale here, this is 0.5 millimeter. This is one of those Martian rocks, and we can identify the minerals within that rock. Just on Earth, we have a series of minerals in our basalts. Mars also has them, and we actually can recognize that Mars has the same minerals in its basalts as Earth has in our basalts. So being on another planet doesn't mean that the chemistries of these rocks or the mineralogies of these rocks are different. Crater counting tells us that the surface of Mars is particularly old. Crater counting is a science where you count the number of craters over an area and then you ratio it to the moon's amount of craters. So the moon has a very old surface. We know that very well. So the moon's surface is very old. It has a certain number of craters. Then you can estimate the age of other planetary surfaces by the number of craters there. You can actually see there's a river system in here as well. There's one, there's another one running down through here. So Mars has had water on the surface. and some of those river systems have been hit by craters. And because there's heaps of craters on the surface, we know that the surface that's exposed today must be pretty old. Earth's surface, geologically speaking, is mostly pretty young. And as a result, we don't see a lot of the cratering history that we've had. That if Mars has been struck by this many asteroids, and Earth's moon has a very heavy asteroid bombardment history, then Earth will have experienced it too. Just our active plate tectonics have obscured that. Anyway, the point of that is that the Martian surface is really old. Probably it represents the first surface, or portions of it represent the first surface of the planet. So, just to summarize so far, Earth and Mars are both differentiated planets. That is, they have a core and a mantle and then a thin crust on the outside. We know the composition of portions of Mars because we have Martian meteorites that have been blasted off Mars and have been picked up from Earth. They show us that predominantly the rock type is basalt. Some of the rovers show us that there are reworked sediments on there. These represent lake sediments. And the very, very old surface implies that it does not have plate tectonics. So that's a very different process to what shapes Earth's surface. Plate tectonics plays a critical role on Earth, but on Mars, there seems to be very little tectonic activity. So this should cut to a video. Here we go. I don't think there's sound, but this is a rocket taking off last July. This is the Perseverance mission, and in the top of this rocket is a rover that has successfully been deployed. It's quite satisfying watching a rocket take off. Here we go, and you can see that it's blowing out. It's burning huge amounts of fuel, and it's accelerating, trying to get up to escape velocity. It's trying to get to a point where it can escape Earth's gravitational field. Incidentally, you can see why it would be difficult to get something off the surface of Mars. To shoot a rocket up requires getting a lot of fuel down onto the surface. And that's probably proving to be a rather difficult point about if you were to get people onto Mars, how on Earth do you get them back off? Or how on Mars do you get them back off the surface? So that rocket, when I first gave the talk, had not reached Mars yet, that we were still seeing it having traveled there. It's now successfully reached the red planet. Various bits of it, or the lander portion of it, has been successfully deployed. We can stop that now. Right, so here is an image of Google Earth. This is the computer program. And what we can do, and I apologize for the quality of this, but what we can do is we can go up to the top up here. This is just a video. We can click Google Mars, and Google Earth will change from showing Earth to showing the red planet. Wait for the computer to get happy. And what I've typed in here is to go to a place called the Jezero crater. We'll zoom back out in a moment. But the Jezero crater, which apparently means lake in Slavic, is where the Perseverance mission was targeting. This is a small crater in the scale of things, and you can make out the shape of it here, a circular shape. There's some good satellite imagery. We'll have a look at that in just a moment. But this is the target for the Perseverance mission, the Jezero crater. For comparison, or to get an idea of the scale of things, this is Lake Taupo, and I've measured the length of Lake Taupo from Taupo village to this southwest corner, and you can see that it's about 40 kilometers across. Well, I do the same for the Jezero crater from this point to this point, and it's also, you can see down here, it's about 46 kilometers across. So this crater is about the size of Lake Taupo. So there is the ability to be able to launch a rocket from Earth and land a lander within a 46 kilometer diameter crater. So it's shoot something to another planet and get it in something the size of Lake Taupo. It gets even better than that. They actually had an even more precise landing point for it, and I'll explain that in a moment. This is another video which shows some of the superb quality of the image of the surface of portions of the surface of Mars. And we're going to zoom in just up into this area in here. But before we do so, just look at this feature here. This is a canyon, and that canyon evidently had water that flowed into this crater, and here are the sediments deposited around. This is a delta. This is an old delta preserved in the Jezero crater. So let's have a look at that video. We're going to zoom in here just to see the quality of the imagery of the surface of Mars. So we're zooming in here. You can actually make out within this channel that looks like water, but it's actually sand dunes because the water's gone. But this surface, we can make out individual sand dunes filling in this canyon. We can go even closer. And you can see here are the sand dunes. I should have put a scale on here, so I'm not entirely sure what they are, but we can see that these dunes are moving across a harder rock surface. Within the canyon, there are lots of dunes effectively mimicking the effects of water as they move through, or giving the appearance to the satellite imagery. And here is a larger dune sitting on the surface. I think it's a larger dune sitting as well. So this particular crater has, just move forward, that was up there. This particular crater has evidence for water having flown into it. And on this side here, we actually have water having flown out of it, although it's been covered by dust that's accumulated here. So the crater is probably pretty old. A little bit closer in, you can see this spectacular large crater. Here's the water flowing out into, or the trajectory of where the water would have flown out into the delta. There's a large meteorite crater that's hit that delta. So the number of craters in here tells us that this lake must have evaporated a long time ago. But this is where the Perseverance mission is targeted. And right now, the rover is somewhere in this area in here. If you were going to another planet to look for evidence of past life, going to a place where there's a former delta would make a really good place to go. One more video. So this is a flight over the Jezero crater. We can see the crater morphology there. This is the outlet to that crater. So there was a canyon outlet. There was also the inlet is on this side over here. Over here. And this yellow circle represents the area. There's that delta. This yellow circle or ellipse represents the area that the Perseverance mission was targeting and where it successfully landed. So currently there is a rover driving around the surface in the crater at that spot there, trying to use its geological knowledge to work out whether there is evidence for past life on the planet. Stop that there. This is it. This is Perseverance rover here. It looks very, very similar to the Curiosity rover. It basically is the same with probably some upgraded componentry on it. But the neat thing about this particular mission is that not only is there a rover, but there's a little helicopter. The helicopter is called Ingenuity. This is it down here. The helicopter weighs about 2 kilograms and it has 2 rotating blades. This is one of them, this is the other, and they rotate apparently in opposite directions to help give it lift, because of course the atmosphere is a different thickness, is weaker than or thinner than Earth's. It's basically a drone, and that's really convenient because if you're a rover and you come up to a rocky area, you either have to go around it or retreat. And so having a drone will give the ability to fly ahead and look at terrain and take photographs and really plot courses much more easily. This is an image recently taken of that rover, Perseverance. This is what the landing site, or very close to this landing site, looks like. It looks like a desert. There are large boulders scattered around, which have been interpreted to represent flooding events, which have moved the larger boulders. And then there is dust and sediment scattered around the surface. This is a real image taken from that rover, and you can see those large boulders just lying around on the surface. And I inserted this image after it tried to take its first core. So the thing about the Perseverance rover is it has the ability to drill rock cores out of the rocks and store them in its belly. And I think the idea for this is, the idea is for this is that it will mean that you need to have a return mission to collect those cores. So right now, the rover will collect them and stick them in its belly and save these 40 cores preserved in there that have been untouched by human hands. Then something will collect those cores in the future, try and get it up to some sort of orbiting spaceship, and then that spaceship will bring those cores back to Earth, where they'll be opened in a clean environment and tested for signs of life. And the reason for this sort of protracted procedure is really quite clever. One of the problems about bacteria on Earth is that it can survive in space for a short period of time. And so it's quite possible that if your rover was not perfectly clean at the start, it could bring Earth bacteria with it to Mars. And then if it drilled a core and stuck it in its belly, it could transfer that bacteria to the core. And then if humans were to pick that core up whilst on Mars and handle it, they could add their bacteria to it as well. And eventually, when it gets analyzed back on Earth, you would say, oh, there's life on Mars. There was life on Mars. It looks like life from Earth. But that would just be because of that contamination. Now, many of the missions haven't been very clean. That is, the rovers were not cleaned at the start, but the Perseverance mission was. The interior was treated in a sterile environment, so there should be no bacteria on it. So by not handling these cores at any point, having humans not handle the specific cores at any point, means that they stand the best chance of coming back here and being able to provide signs of life without any kind of cross-contamination. The first core they drilled was actually a complete disaster. You look down, this is the camera looking down the hole. Yep, this is a hole on Mars drilled by a robot geologist. And the thing is that the storage device, the area on the rover is supposed to be able to tell whether there is anything in its core tube. So it stores the cores in tubes. And the first core they drilled, they didn't have any change to the weight of the sample canister. So the first time they drilled a core, it just crumbled into thousands of little fragments. And this is the camera looking down the hole, trying to find out where that core's gone. But the reality is that the core just pulverized itself into this debris. Subsequently, though, they've managed to successfully collect cores. I include this as just a short little video showing the rover taking an image of Ingenuity. This is the drone helicopter. So you can see it's two rotating blades. And it does fly on Mars, which was one of the questions. So would you actually be able to fly a helicopter on Mars? And the answer is with careful engineering, it can be done. So the Perseverance mission's goals really were to test for present, or really were to test for past life. Or, if you found present life, that'd be pretty cool too. But really it was to examine past life, go to a delta, look for rocks that could have had past life, because on Earth, lakes are great places for life. I suspect if they find it, and I think they genuinely think that life will be found on Mars, that it will be fairly simple life. It looks like the ocean on Mars was present at about the time that life on Earth began, but we know that life on Earth took a long time to evolve into complex multicellular bodies. So probably Mars will have fairly simple life if it has any at all. One point of difference could be that the permafrost, that's the frozen ground, is relatively shallow, and that would be protected from the solar radiation. And so there could be life beneath the permafrost. But the key thing is that the surface is being bombarded by radiation today, and it will be for its foreseeable future because it has such a thin atmosphere. So the chances of complex life on Mars, I think, are slim, or the chances of that being achieved, I think, are slim. In terms of complex life, you need essential elements, so carbon, hydrogen, sulfur perhaps, but the mission was really going where there was water, and we know that there was water on Mars and quite a lot of it, and the Jezero crater is a superb example of that. So to summarize, what is Mars made up of? Well, at the surface, it's predominantly basalt. That's a volcanic igneous rock that many of you will be familiar with. It also has sedimentary rocks, which represent lake floors, where the water is evaporated. How old is the surface? Well, the abundance of the craters really point to it being an old surface. And even some of the meteorites that come back, which have been dated, so that's the time, determined the time at which the meteorite formed, show that some of the rocks that have come back today are almost 4.5 billion years old, which is very close to the formation of the planet. So the surface of Mars still must have a lot of very ancient rock, the first crust on it. What is the interior of Mars like? Well, broadly, it's chemically known to be similar to Earth, but it has a different history to Earth. It hasn't had plate tectonics disturbing it and stirring it up. So whilst the interior can melt and produce basalt, like we have on Earth, it has a different tectonic history. It doesn't have plate tectonics. How does it compare to Earth? So we can say that both of them have basaltic volcanoes. They have different sorts of tectonics. Earth has liquid water at the surface, and Mars had it in the past. The chance of life, I'm guessing probably zero, except perhaps the bacteria on the landers. But I would say that it was probably life early on. I'll put it out there. The issue for the lack of life is that no magnetosphere, there's no strong atmosphere, and that equals no life. But that doesn't preclude what was the case in the past. I should say, before I finish, I think this is the last slide, that the lack of the magnetosphere is a major problem, and it's a major problem for us if we were to go to Mars. The lack of the magnetosphere means that it would be very difficult to build a thick atmosphere and change the composition of the atmosphere from CO2 rich to nitrogen and oxygen rich, something that we could breathe. If we were to go there, we wouldn't be able to take off our helmets. The room that you're sitting in at the moment probably represents the maximum amount of personal space that you would have on the planet. And the gravitational strength is weaker than that of Earth. And we know that astronauts that go into space, they're in the space station, for example, have to train very hard to keep their bone density. Whilst that's not quite as extreme as, well, Mars is not quite that extreme, you'd have to do a bit of exercise to maintain your bone density if you're going to be there for a large period of time, unless the gravity could be changed somehow, and Mars is too small for that. So the chances of humans living on Mars are, it could be done, but it would be difficult. It wouldn't be as easy as just packing up here and going there. We can't even build structures on the surface. And that's because our main building things here, you can think of concrete. Well, there are the components that make up concrete on Earth are almost absent on Mars. There's so little water at the surface. There's a little bit buried beneath the surface, but it's lost a lot of water. So even having the ability to make concrete would be difficult. And then, of course, we would need steel to reinforce the buildings from Martian winds. Or we could live in tunnels, lava caves, but that wouldn't be very satisfying, I think, not on a long term. So yeah, I'll just conclude with that. This is just how on Earth we can tell what Mars is made of. So I will close that.